Okay, I hope they can hear me now. Okay, yeah, apologies for this. I hope we can make it up in the, well, I hope we can make it up in the seminar. Yeah, so for anything that remained unclear. Okay, anyhow, so maybe I just briefly repeat what we're doing here. So we're introducing over the barrier ionization, and the idea is that if the field is sufficiently strong, the laser field, that the force that it actually suppresses the Coulomb potential, or this remaining potential below the ionization potential. Yes, that then the electron is free to leave the atom. And this we call over the barrier ionization, and it occurs at a certain field strength that we call over the barrier field strength, EBS. Yeah, and this is what we want to calculate now. We're writing down the total potential, taking the derivative with respect to x in order to find the point xb. And then we calculate the field strength at this, actually the value of the potential at this position, and from there the field strength that's required to suppress the barrier. Okay, now this is the potential now at xb. So 1 over 4 pi epsilon 0, then we plug in the value for xb, we still have ze there, then square root 1 over 4 pi epsilon 0, z over e. Maybe it helps when I scroll down here. So this is E naught, and then we have the term for the laser. Okay, so this, if you summarize this, you get 2 times square root z times E naught times E divided by square root of 4 pi epsilon 0. Okay, now in case of barrier suppression, the value of V of xb must be smaller than or equal to the ionization potential. Yeah, then the barrier is completely suppressed. Keep in mind here that the ionization potential is defined such that it has a negative value. And then this equation here makes sense. Okay, so we have EIP equals 2 square root z E naught E over 4 pi epsilon 0. Now we rearrange this for E naught, and we get 4 pi epsilon 0 over z times E squared times EIP over 2 to the second power. And as always, this becomes much easier if we use atomic units. Then we simply have 1 over z times EIP over 2 to the second power. Yeah? And this would be the barrier suppression field strength. Maybe more useful is the barrier suppression intensity. So the intensity where the peak of the field reaches this value. That's the barrier suppression intensity, BSI. So we use here that the intensity in atomic units is simply given by the square of the electric field. IBS equals EIP, sorry, not squared, but to the 4th power. Sorry, not EIP. barrier suppression intensity. So in EIP there's a square root missing? 4 pi epsilon 0 z over E. Above it. There's a square root missing. Down here, yes. Thank you. Absolutely. Yeah. Okay, the barrier suppression intensity, so we simply square this here and we get EIP to the 4th power divided by 16 times z squared. So the unsurprisingly, this value depends strongly on the ionization potential. Yeah, this we expected that because well, the deeper the bound state is, the higher the field strength must be in order to suppress it. It's indeed a very strong dependence here with the 4th power. And what we also find is that it depends quite strongly on the nuclear charge. Yeah, in particular, when the more highly charged the system is, the easier it gets to suppress the barrier. However, of course, the ionization potential also increases strongly as you go to highly charged ions. Yeah, so this actually still dominates, as we will see. However, for excited states of ions, this might be very different. Yeah, because excited states can actually have low ionization potential. Now, we should now this barrier suppression intensity, an important consequence of it is that, speaking of tunnel ionization, is only meaningful if there is actually a tunnel to go through for the electron. Yeah, if the potential is completely suppressed above the barrier suppression intensity, then there is no tunnel and therefore no tunnel ionization. Yeah, so speaking of tunnel ionization, yeah, so I'm talking about tunnel ionization here, is only meaningful for intensities, well, smaller than the barrier suppression intensity. Yeah, so as I said in words, it only makes sense if there is a tunnel to go through. Yeah, let's do a quick example. Of course, we choose hydrogen. Yeah, so example H. So we have an ionization potential of 0.5 atomic units, and now we need to plug in the number for Z here. Now, the hydrogen atom is of course not charged, yeah, but what we refer to is actually the charge of the ion that is left behind after ionization. So our example is actually the ionization of neutral hydrogen atoms to hydrogen ion plus 1 electron. Yeah, and then we can calculate the barrier suppression intensity. EIP is 1/2. Yeah, so this is 0.5 to the 4th power. So 1/16 divided by 16. Yeah, so yeah, I calculated that right, didn't I? So to the 2nd power would be 1/4, to the 3rd power would be 1/8. So 1/16 over 16. So this is 1/225, or 0.0039 atomic units. And that corresponds to an intensity of 1.37 times 10 to the 14 watts per square centimeter. It might be, hang on a second, did I put this on a table here? No. Okay, it might be interesting to actually compare different systems, different atomic systems, let's say. So for the rare gases, which are often used in strong field experiments because they are simple atoms and they're pretty much the only gases that exist in the atomic form. So we have here the gas, the value of the ionization potential, and then the numeric value of the barrier suppression intensity in units of watts per square centimeter. And yeah, so we have helium, the ionization potential, so this is in units of electron volts. The ionization potential is 24.6 eV, and for this we get a barrier suppression intensity of 1.46 times 10 to the 15 watts per square centimeter. Then we have neon, 21.5 eV, 8.6 times 10 to the 14. Argon, which is really the only cheap rare gas, 2.5 times 10 to the 14. And now come the expensive things. Yeah, krypton, 14 eV, and 1.5 times 10 to the 14 watts per square centimeter. Then we have xenon, which is the easiest to ionize if you neglect radon, which you don't really want to use. 8.7 times 10 to the 13 watts per square centimeter. And now, for comparison, if we had the ground state of xenon plus, where the ionization potential is 20, it's actually pretty close to 21 eV, so close to neon, but because of this Z squared dependence in the denominator, we actually arrive at 1.9 times 10 to the 14 watts per square centimeter. Yeah, so much lower than the value for neon. Okay, so this is our third mechanism, barrier suppression ionization. So let's order our little zoo a bit. Yeah? And this is done by introducing the Keldysh parameter. But let's first get an overview. So parameter ranges and ionization mechanisms. Okay, so let's draw a picture. So the first process that we introduced was multiphoton ionization. Okay, and well, this is supposed to be symmetric. So this is the continuum, this is the ground state, and now we absorb multiple photons. Yeah, this was the first process, multiphoton ionization. Then we had tunnel ionization, where we actually have this laser potential here, and then we have this suppressed barrier where the electron can tunnel through. Yeah, and this would be our tunnel range. And finally, we have a barrier suppression ionization where the barrier is so strongly suppressed that there is no more tunnel to go through. Now, the question is, what mechanism should be, like, how should we picture our ionization process? And for there's basically a distinction between these ranges and those ranges, and this will well, this actually was we already mentioned in our comment up here. Introduced to. So yeah, this comment here. Yeah, speaking of tunnel ionization is only meaningful below the barrier suppression intensity. Okay, but when should we talk? When should we think about multiphoton ionization? When should we think about tunnel ionization? And this is the Keldysh parameter, 3.21 Keldysh parameter. And before we derive this, we briefly switch to the PowerPoint presentation, please. Yes, and we'll take a quick look at or remind ourselves of the ponderomotive potential. Because once again, yeah, as for the final energy of the electron, the ponderomotive potential is the important scaling parameter here. Yes, and you see here that it depends on intensity and frequency of the light. So our standard example was the 800 nanometer titanium sapphire laser, where at 10 to the 14 watts per square centimeter we have a ponderomotive potential of 6 eV, approximately 4 times the photon energy. Yeah, and then if you go to mid-IR laser instead, for example 3.2 micrometers, then the photon energy is only 0.4 eV, but because of this lambda squared scaling, or 1 over omega squared scaling, we have a ponderomotive potential of 96 eV, which is really much, much higher than the photon energy. So here you might expect that the photon character of the field is really not that important. The counterexample would be a free electron laser. So an extreme ultraviolet free electron laser, for example, FLASH in Hamburg, where, well, this actually consists of a long linear accelerator followed by an undulator, and then this can produce intense radiation at, for example, 13 micrometer wavelength. Yeah, so the photon energy is here something like 90 eV. And we can calculate easily that the ponderomotive energy is only 1.6 milli-electron volts. Yeah, so in that case, this oscillatory motion of the electron is probably negligible is obviously negligible compared to the photon energy. An even more extreme example is an X-ray free electron laser, where there is currently only one in the world, really, namely LCLS in California. And here one can achieve much higher intensities. Yeah? So this is 10 to the 18 watts per square centimeter, for instance. And however, the ponderomotive potential then is only 36 milli-electron volts. So again, much, much smaller than the photon energy. Yeah. Okay, now back to the iPad. Yeah, so we'll keep these numbers in mind, that they are very different regimes. And we again go back to our hydrogen atom. Yeah, so consider H atom in electric field. Yeah, so it's basically this. So this kind of configuration, and the question that we want to answer is: when should we picture it like this, or like that, or like that? Okay. So as already mentioned, the first thing is so barrier. So OBI over the barrier ionization, or barrier suppression ionization. This should be considered for intensities larger than the barrier suppression intensity. And we should keep in mind here, however, that the electron cannot move instantaneously. So if we have a very high frequency field, for example, an X-ray field, then this picture might also be wrong. Because probably a typical time scale for the motion is the Kepler period. So if you picture a Bohr model of the atom, then the electron takes, for example, in the hydrogen atom, 150 attoseconds or so to go around the nucleus. Now, of course, the Bohr model is oversimplified. However, there is some kinetic energy with the electron associated with its ground state. So it's not completely pointless to say this. So maybe I put a little warning sign here. Electron velocity is finite. With regard to high frequency fields. However, for high frequency fields, obviously the photon energy is very large, and therefore single ionization is probably what happens, and we don't even need to consider these processes at all. Okay, so before the barrier is suppressed, the electron can tunnel. So this is for intensities smaller than the barrier suppression intensity. And this you can picture, so this type of tunnel ionization, like if you imagine that the electron velocity is much, or that the time scale of the electron motion is much shorter than the optical period, then you could think of the potential as being completely static and the electron tunnels through. This would be equivalent to field ionization, as occurs, for example, in tunneling microscopy, where you move this tip over a surface, and there, of course, everything is really slow. And at a very slowly varying field, which means long wavelength, we could consider a similar process. And this is also sometimes referred to as optical field ionization. OFI. So we don't really use this abbreviation anymore. Okay, an important difference, however, is that in our case, the field actually varies. So the field is non-static. And then, of course, tunnel ionization, so the field is non-static, and this means that the potential varies with time. Potential V equals, so it's a function of time. And the fundamental idea here is that the concept of optical tunneling only makes sense if the time scale of the electron motion is fast enough to that it can actually move out of the atom while the tunnel exists. Because a quarter cycle after the peak of the field is reached, we're back to zero field, and then there's no possibility to tunnel. So clearly, tunneling is only meaningful if, the variation of the potential variation V of t is slow compared to the electron motion. Yeah, and this is expressed by the Keldysh parameter fundamentally. Keldysh parameter. I call this gamma tilde here because this is slightly different from the value that we will derive here is actually slightly different from what is found in the literature. So this would be then the tunnel time, if you allow me to call it like this, divided by the optical period. We call this tau tunnel divided by the optical period. And this should be smaller or much smaller than 1 for tunneling. And now, of course, we want to find an expression for this tunneling time. Find tau tunnel. Okay, so we begin by expressing or let's say by writing the kinetic energy of any particle, mass over 2 times velocity squared.
So is this potential
Yes, so this is the total potential, yes? The potential, this potential V of t here, this is the total potential given by the atom and the laser. The atom, however, doesn't change actually. So it's the potential of the laser, yes. Yeah, so the... So what's the... Yes. Exactly. The changes of the potential are given by the variations of the external field.
Yeah, but the potential is also a function of the distance from the atom?
That's true, yes.
So should be also a function of x and t?
Right. So we're considering here the case where the electron is bound, right? So we consider the case where the electron tries to tunnel. Yeah, if we allow the electron to have a will. Yeah, and there it doesn't really it's bound, so the position is more or less fixed. And yeah, so and this is why the time scale at which the potential varies is given by the optical period. Okay. Now, with this equation, of course, we can write the velocity as square root of kinetic energy over mass. Well, there's a factor of 2. And now we still need an expression for the kinetic energy. So let's quickly picture a little a typical tunneling scenario. Yeah, so you have here some potential barrier. And now you have a particle with, so what we're actually plotting here is the energy of a particle. Yes, and then we have a particle at some energy and some energy there. And here we have our barrier. Now, in this region here, the kinetic energy is equal to the total energy of the particle because the potential is 0. Same applies, of course, here. And in this region, actually the kinetic energy equals the total energy minus the value of the potential, and that would then actually be smaller than 0. Now, if we plug a negative value in here, we get a complex velocity. Yeah, so this So this is a complex number. Okay. That's of course a little bit difficult to picture. Yeah, but for this estimate, we'll just pretend that everything is fine. Okay, so now with velocity equals change of position over time. Yeah, we can write time as the change in position over velocity, and now we plug in our value for the velocity, this one here. Oh, actually we'll use the kinetic energy. Yeah. Or if we allow for the kinetic energy of the particle to change, then we should write it in a differential manner. So we have mass over kinetic energy dx. Okay, and now, so if we find an expression of the kinetic energy dependent on the position in the potential barrier, then, no, it's actually inside, yeah, because the x here is also inside. Is it? No, you're right. Yeah, so we'll plug this in here. Yes, thank you. That was nonsense. Okay, yeah. So yeah, so we can, if we integrate then over x, yeah, we can use this here to find the value for the time. And first, before we do that, we'll make a little simplification because we don't really want to integrate over Coulomb potential. Simplification. Yeah, so oops, it's not a, was supposed to be a delta potential. Yeah, this would look something like yeah, so if you actually zoom out far enough, yes, then what the total potential looks like is this here. Now here's the center. It's very narrow, and yeah. So if we zoom out far enough, this Coulomb potential actually looks like a delta potential. And then this tunnel region here is actually just a triangle. Yes. This here would be the ionization potential, and this slope here is minus E, so this is minus E times x. And then we can find an expression for this point. Yeah, so here we have minus x times E equals minus EIP. And therefore x, yeah, this would be the tunnel exit in this delta potential. This would be EIP divided by the electric field. And now we can use this expression here. And we'll write that the tunnel time, tau t, equals the integral from the tunnel entrance to the tunnel exit, which is EIP over E. Yeah? So this point here times square root m over 2 E of x, and that's the kinetic energy. And yeah, so this can be solved easily. Square root of m over 2 goes out of the integral. We integrate from 0 to EIP over E times 1, this is the square root, 1 over EX minus EIP dx. Okay, now again, this is a negative number. Yeah, EX minus EIP inside the tunnel is negative. Yeah, so this is complex. So the square root of minus 1 is of course I. So we'll take an I out of this. Out of the square root here, and then we can actually take solve the integral. Yeah, because this has the exponent minus 1 over 2. This is where this 2 comes from, and the minus goes here. And then we have the solution of the integral in the limits from 0 to EIP over E. And then we plug in the limits. 2m over E squared. Yes, this is 0. Yes, so at the upper limit it's 0. At the lower limit it's square root of EIP. And so we get in atomic units that the tunneling time, tau t, 2 EIP over E squared square root. And this is a complex time, yeah, whatever that means. And we'll use this value nevertheless to now calculate our modified Keldysh parameter. Yeah, so we have, we'll use the modulus. And this would then be 2 EIP over E squared. And we'll write the 1 over the optical period, we'll write as omega over 2 pi. And this gives us 1 over 2 pi EIP times omega squared over electric field strength. And now, yeah, so we have here E squared and omega squared. We're quite familiar with this. So this is a quarter of the ponderomotive potential. I'm missing a 2. Yeah, so I'm missing a 2 here. And our result is 1 over 2 pi. Maybe I'll write this down here. UP. Oh, sorry, it's actually one. So if I write, I make it easier. EIP omega squared E squared, and now I write a 4 here and a 4 there, yes, and then this here is 1 over UP, and so we can write this entire expression as EIP over 2 UP. Yeah, so once again, UP shows up here as a scaling parameter. Yeah, so I mentioned that in the literature one finds a slightly different definition or result. In the literature, we have gamma equals square root EIP over 2 UP, and this equals exactly 2 pi times our definition of the Keldysh parameter. Okay, so and now for the interpretation, yeah, so yeah, for gamma smaller than 1 or much smaller than 1, in practice it's actually used as just smaller than 1, though one can discuss about this. Yeah, so for gamma smaller than 1, it is reasonable to speak of tunnel ionization. And for gamma much larger than 1, we have multi-photon ionization. That would be the better picture then. Okay, we'll do a few examples on the PowerPoint slide, please. Yeah, so what do we have here? So here are some values for the ponderomotive potential for different atoms and different intensities for 2 different wavelengths. So on the left-hand side in the table, we have 800 nanometers and various intensity values. And you see that for that at low intensities we have we're more or less in the multi-photon regime, and only at high intensities we reach maybe the tunnel ionization regime. However, you actually see that these values are always close to 1. So if you really want to study tunnel ionization, you should use long wavelengths, as you see on the right-hand side. Yes, so for 3.6 micrometer wavelength that we have here, these values are, the values for gamma are essentially always significantly smaller than 1. Yeah, in particular for the higher intensities, but also at moderate intensities, these values are significantly smaller than 1. And however, one has to take care that the barrier suppression intensity actually gives somewhat of a limit to the reasonable, to whether you can actually speak of tunnel ionization or whether there is no tunnel to go through. Yeah, so for example, for helium, we calculated just over 10 to the 15 watts per square centimeter as the barrier suppression intensity. So there, even with 800 nanometers, you can speak of tunnel ionization. However, for example, for xenon, where the barrier suppression intensity is below 10 to the 14 watts per square centimeter, you see that you can't really speak of tunnel ionization. Nevertheless, when you read the literature, you often find this situation. Yes, you often find tunnel ionization being assumed there, and that's not strictly, that's arguably incorrect. Yeah, so this, I need to see what's the next. That comes later. Okay, so one more remark regarding this barrier suppression intensity, and then we'll take a break. So back to the iPad, please. So let's just so remark the barrier suppression intensity can be seen as sort of an optimum maximal intensity to reach tunnel ionization. Yeah, or how Professor Paulus likes to say, maximal förderliche Intensität. Yeah, similar to maximal förderliche Auflösung. The BSI can be seen as a maximum, let's say maybe useful intensity to achieve tunnel ionization. Oops. Okay, for whatever reason you may want to achieve that, yes. So we can actually define a minimal gamma parameter. Yeah, and so this would be basically the gamma that you have at the maximum at the barrier suppression intensity for a given atom and a given laser. Yeah, so a given wavelength. So let's call this 2UP max. No, gamma minimum is then EIP times 4 omega squared over 2 barrier suppression intensity square root. Now we plug in some values and we find the expression 32 omega squared over EIP to the third power. And well, since we earlier on we compared the free electron laser to our optical lasers in terms of the ponderomotive potential. So let's briefly do this also for the Keldysh parameter. What about X-ray FEL? Yeah, so for flash, which is at which operates at 13 nanometers or so, we had UP equals 1.6 milli-electron volts. Yeah, and then gamma, if we assume hydrogen, would be 65. And for LCLS, where UP is a little bit larger, 36 or so milli-electron volts, gamma would be 13.8. In any case, both of these values are much larger than 1. Yes, so one would see multiphoton ionization as the proper picture in case one even requires multiple photons in order to ionize. In any case, one would expect perturbative behavior in the case of these short wavelengths. Okay, yeah, so we'll return in 5 minutes for the next lecture. Thanks so far.